Today, we depend on modern, well-marked highways to get us from one place to the other. But without a destination, even the fastest road would get the traveler nowhere. Wastewater also must follow a planned route and have a final destination. That is why it travels to various stages of treatment under the careful supervision of the treatment plant operator. Now, after wastewater has passed through the preliminary treatment stage, grit and screenings have been removed. However, the wastewater still contains copious amounts of solids that also need to be removed and treated. In addition to wastewater passing from the preliminary treatment stage, wastewater that is flowing from a biological treatment unit will contain solids that need to be removed as well. The process of removing settleable and floatable solids from the wastewater is usually accomplished with a treatment unit known as a clarifier, which facilitates a process called sedimentation and floatation. The main job of the sedimentation and floatation process is to remove settleable and floatable solids by greatly slowing the velocity of the wastewater while providing a placid environment where many solids will either settle or float. After the solids settle out or float to the surface, the clarified wastewater flows over the effluent weirs onto the next stage of the treatment process. Clarifiers are usually round or rectangular in shape and can vary in size depending on the design flow of the wastewater treatment facility. Clarifiers can be found at different stages of the treatment process. You may find a clarifier in the primary treatment stage just after the bar screen and grit removal. These units are known as primary clarifiers, and they clarify the wastewater before it is passed on to the next stage in the treatment process. It should be noted that primary clarifiers do not remove all solids. There are still colloidal and dissolved solids that must be removed by some type of secondary treatment unit. Secondary clarifiers are located downstream of a biological treatment stage. In advanced facilities that have more than one biological treatment stage, an intermediate clarifier separating the two biological treatment processes may be found as well. The clarifier following the final stage of biological treatment is usually known as the final clarifier. In any event, the solids removed from a secondary clarifier are different from the solids removed in primary clarifiers. The settlable solids removed from a primary clarifier tend to be much denser than those removed from a secondary clarifier. Biosolids from primary clarifiers may also exhibit anaerobic or septic conditions as opposed to aerobic secondary biosolids. The floatable solids in a primary clarifier consist of grease, oil, hygiene products, and other materials that will float. Floatable solids found in a secondary clarifier are usually oxidized organic matter found from the preceding biological treatment stage. If clumps of floating biosolids are found on the surface of either primary or secondary clarifiers, it indicates that the biosolids are remaining in the clarifier too long. Biosolids removal rates should be checked and increased if necessary in order to prevent the biosolids from rising. The collection mechanism should be checked for malfunctions as well. In some cases, the solids in the hopper tend to hang up, and it may be necessary for the operator to use a long pole or squeegee to scrape down the walls of the hopper. Care should be taken when scraping solids from the walls of a hopper to prevent excessive turbulence. Now let's take a closer look at clarifier design. A rectangular clarifier is usually used as a primary clarifier. If there are multiple clarifiers, the influence should be distributed evenly to the clarifiers. When the flow enters the clarifier, it first runs into a baffle. The purpose of the baffle is to slow the velocity of the wastewater and to distribute the wastewater evenly through the clarifier. Without the baffle, short-circuiting would occur. The collection mechanism is a continuous chain and scraper assembly that travels slowly while scraping the settled biosolids into a hopper on the bottom of the clarifier. The mechanism then travels to the surface where it collects and moves the floatable solids to the scum removal device. In most cases today, the chain on the collection mechanism is made of a strong plastic material, and the flights or scrapers are made of fiberglass. Even the sprockets being used today are non-metallic. In older clarifier units, you may even find metallic chains with redwood flights. Be sure to check the operation of the collection mechanism regularly. Observe the movement of the chain and scraper mechanism. It should be fairly smooth, not jerky. Be sure to look at and note the condition of the chain, wear shoes, and flights. If the motor and the gearbox run, but the collection mechanism does not, it could indicate that a shear pin or chain may be broken. To determine what the problem may be, observe the drive chain. If the drive chain is moving and the collection system is not, it probably indicates a broken chain on the collection mechanism. When the drive chain breaks, it may be missing altogether. If the motor and gearbox are turning and the drive sprocket is not, the problem most likely is a broken shear pin. Shear pins tend to break more frequently in winter months when ice on the clarifier surface interferes with proper operation. An excess of solids in the clarifier, the presence of debris, or a mechanism jam can cause a shear pin to break as well. In any event, the cause of the shear pin failure should be determined before restarting the mechanism. Restarting the mechanism with a heavier shear pin is not the answer and could cause serious damage to the collection mechanism. If the motor fails to restart, it could indicate a variety of problems, such as an open disconnect switch, a motor starter that may need resetting, an electrical circuit breaker in the off position, or that the motor itself is defective. In any event, the problem needs to be diagnosed and corrected. The proper operation of the scum removal equipment is also an important element in the performance of the clarifier. Any problems with the scum removal process should be identified and corrected immediately. Timely removal of floatable solids or scum is an important function of clarification. If floatable solids are not removed, they will flow to the secondary treatment process or ultimately contaminate the facility effluent. This is a problem especially with trickling filters, as the floatable solids will clog orifices and media. Disposal of the floatable solids can be a problem as well. In many cases, floatable solids are placed in an aerobic or anaerobic digester. These solids present a particular problem in anaerobic digesters because they increase the depth of the scum blanket, resulting in the loss of valuable digester space. Some anaerobic digesters are equipped with a mixing capability, which helps in breaking up the scum. The microorganisms contained in the digester prefer to eat most other organic matter before grease. If scum in the anaerobic digester becomes a real problem, it may be more effective to dispose of it by means of incineration or have it directed to a permitted landfill. The effluent weirs should be level and clean, allowing an even flow of wastewater to discharge over the entire course of the weirs. Measures should be taken immediately if weirs are uneven, clogged with solids, or become leaky. Now let's take a closer look at circular clarifier mechanisms. In these units, the wastewater enters through the center column and into the influent well. The influent well is a baffle that slows the velocity of the wastewater and distributes the wastewater evenly throughout the clarifier. As with rectangular clarifiers, the operation of the sludge and scum mechanisms should be observed closely. Circular clarifiers may have a mechanism that consists of blades or scrapers that move the sludge towards a hopper in the center of the clarifier. The floor of the clarifier is usually sloped towards the center of the clarifier. The unit should be inspected for missing or maladjusted scrapers. The circular clarifier unit usually has a scum collection mechanism as well. Circular clarifiers have an over-torque device that will disengage the unit in the event of a jam or overload. Some circular clarifiers that are designed for settling activated sludge may have pipes that sort of vacuum the activated sludge from the bottom of the clarifier. This type of clarifier unit can operate with pumps either hydrostatically or off of differential head. In either case, removal of the biosolids in this fashion is necessary because the activated sludge tends to be light and does not compact as well as primary sludges and is therefore difficult to move effectively with scrapers. As with rectangular clarifiers, you need to pay close attention to details such as solids removal rates, scum removal, and the effluent weirs. You may also see very small square clarifiers in package-type treatment plants. These clarifiers usually do not have a sludge collection mechanism, and the tank slopes into a very steep-sided hopper where the sludge is removed. Typically, both sludge and scum are removed with an airlift type of solids pumping system. Other types of clarifiers that combine primary clarification and solids digestion in the same unit may be known as a clarijester or an Imhoff tank. Essentially, the top part of the tank is the clarifier, while the bottom portion of the tank is used for anaerobic solids digestion, and baffles are utilized in order to separate the two processes. You can expect similar clarifier performance from these units when compared to conventional clarifiers, as long as the solids handling portion of the unit is operated properly. The solids handling portion of these units will not be as effective as a properly operated anaerobic digester. Imhoff tanks are rarely used today. Gravity sludge thickeners may have a similar design as that of primary clarifiers. The collection mechanism is beefed up to handle copious amounts of very thick solids. The thickener performs a function similar to that of a clarifier, and its design may even include all of a clarifier's components. Regardless of the type of clarifier, solids removal, both floatable and settlable, is the prime function of the clarifier unit. It is essential for the operator to be familiar with the design and loading conditions of the clarifier in order to operate it properly. Timely removal of floatable and settled solids is necessary for proper operation of the clarifier unit. Most commonly, primary sludges are removed from clarifiers with a positive displacement type of pump. The most common type of pump used for this purpose today is the piston pump. It is important to note that you must have all the necessary valves open before starting a positive displacement pump. Failure to do so will result in serious damage to the pump or to the piping system. As with all equipment, you need to become familiar with the unit by reading and understanding the operating instructions before you attempt to operate that equipment. Centrifugal pumps that are designed for solids handling may also be used for moving or removing solids. The centrifugal pumps are used commonly for removal of secondary sludges and for circulating the contents of primary anaerobic digesters. The majority of solids removed from activated sludge clarifiers will be put back into the activated sludge process, where the hungry microorganisms in the activated sludge will feast on the organic material in the wastewater. A portion of these solids may be wasted into a biosolids handling facility for the purpose of digestion. Primary sludges and trickling filter sludges will usually be placed into a biosolids handling unit, which will facilitate digestion. Before being placed into a digester, the solids may pass through some type of thickener, such as a dissolved air flotation thickener or a gravity thickener, in order to remove as much water as possible. You may find chemicals being added to the influent of some clarifiers in order to enhance performance. With clarifiers that have sporadic heavy hydraulic loadings, the use of polymers may be necessary to enhance the settling characteristics of the solids in the wastewater. The polymer causes the particles in the wastewater to coagulate. thus forming bigger and heavier particles which will more readily settle. The use of polymers can get quite expensive, and it is usually not considered part of normal clarifier operation. For wastewater that exhibits septic conditions, the use of oxidizers such as potassium permanganate or chlorine may help to freshen the wastewater, reduce odors, and oxidize objectionable pollutants in the wastewater. The facility NPDES permit specifically requires the operators of the treatment plant to be familiar with operation and efficiency of each treatment unit. To meet this requirement, operators must perform and analyze process control tests. In order to ensure proper operation of clarifiers, the wastewater treatment plant operator must make frequent visual inspections of the clarifier units, calculate the flow through the unit, calculate weir overflow rates, calculate detention time, calculate solids removal efficiency, calculate surface loading rates, and calculate solids removed from the clarifier. In making these calculations, the operators should account for the variations that occur in daily, weekly, or seasonal flow conditions. At a minimum, the lab tests and data on both the clarifier influent and effluent for calculating efficiencies and removals would include pH, temperature, total suspended solids, settlable solids, CBOD, and flow through the unit. Be sure to include recycle flows. Many operators are under the false assumption that the only lab tests that need to be performed are those parameters listed on the Facility Discharge Monitoring Report. However, proper process control lab testing is required for all treatment units as specified in Part A of the NPDES permit. The NPDES permit specifically states the permittee shall effectively monitor the operation of all treatment and control facilities and the quality and quantity of the discharge. Part B of the NPDES permit also mentions process control testing under facility operation and quality control. Process control testing is not spelled out parameter by parameter as in the DMR, and does not get reported monthly as with the DMR. However, all data for process control as well as self-monitoring must be retained for a minimum of 3 years or longer if directed by state or federal agencies. Proper maintenance of the clarifiers is also a requirement of the NPDES permit. Please be sure to follow all manufacturers' recommendations for lubrication, inspections, and adjustment of clarifier components. Clarifiers must also be periodically dewatered or drained in order to inspect and adjust drive units and to inspect the tank structure and remove debris. Care needs to be taken when dewatering any tank because a high water table can cause tanks to float right out of the ground. And now, only after the wastewater has been carefully and properly processed in the clarifier can it be discharged onto the next stage of treatment at the wastewater treatment plant. A well-maintained, well-tuned automobile is essential for our mobile society. It is a fact that poorly maintained automobiles produce more pollution and are costly to operate. Just like automobiles, trickling filters and rotating biological contactors must be well maintained and tuned to save money and reduce pollution. Trickling filters and rotating biological contactors are carefully controlled biological processes that utilize aerobic microorganisms to consume colloidal and dissolved organic matter from the wastewater. Removal of the colloidal and dissolved solids is necessary to reduce the BOD in the wastewater. In some cases, trickling filters and rotating biological contactors are designed to remove ammonia from the wastewater. In treatment facilities that are designed for ammonia removal, trickling filters or RBCs may be operated in series with another biological treatment unit. Taking a closer look at the trickling filter, we find that it is comprised of four major components: the retaining structure, the media, the distribution system, the underdrain system. First, let's take a look at the retaining structure. The structure houses all of the other major components of the trickling filter. The structure may be either round or square and could be anywhere from 4 feet to 50 feet tall, depending upon the design of the filter. Materials commonly used for the construction of trickling filter structures include concrete and a special ceramic coated steel. The taller filters usually have ladders for easy access. The structure should be inspected regularly and repaired if necessary. Care should be taken to prevent excessive weed growth around the trickling filter structure, as this provides an excellent place for filter flies to congregate. Next, we will look at the media in the trickling filter. The media provides surface area for microorganisms to grow and feed on the organic matter in the wastewater. In all trickling filters, the media is either a stacked type or random dump type of media, such as rock. Random dump media should be uniform in size to facilitate airflow through the media. As the name suggests, this media is dumped into the filter up to the desired depth. Random dump media may also be made of plastic or other materials. Stacked media is generally a plastic media that comes in sections that resemble hay bales. This media is carefully stacked in several layers within the trickling filter. In most plastic media, the top layer has some sort of ultraviolet protection to avoid deterioration due to sunlight. All media should be examined for signs of deterioration. Deteriorating media can lead to poor operation and septic conditions within the filter. The media should also be kept free of debris. Looking at the distribution system, we see that it may be either a rotating or a fixed orifice type of system. In either case, the job of the distribution system is to evenly distribute the water over the filter media. Rotating distributors are usually powered by the jet action of the wastewater discharging from the orifices. A rotating distributor may have either 2 or 4 arms. The orifices are usually adjustable and are equipped with splash plates to evenly fan the wastewater over the media. The orifices are closer together as you get to the outer part of the distributor to facilitate an even distribution of the wastewater over the entire bed of media. In some cases, there may be orifices on the reverse side of the arm to act as reverse thrusters to control distributor arm speed. Most distributor arms have end plates that can be lifted to flush out debris. It is important to keep the flow through the distributor arm unrestricted. Keeping the orifices clean is important for proper operation of the trickling filter in both fixed and rotating distribution systems. In the center column of the rotating distributor, you will find bearings and seals that must be maintained. If the seal in the center column is leaking excessively, it should be replaced. Leaking seals can lead to poor trickling filter performance. Warning: some older trickling filters may be equipped with mercury seals. Mercury is an extremely toxic element that requires special handling. If your trickling filter is equipped with a mercury seal, notify your local DEP office at once. Finally, let's take a look at the underdrain system. It is this system that supports the media, facilitates the collection of the wastewater under the filter media, and allows for airflow up through the media. The underdrain system should be kept free of debris to allow the wastewater to flow unrestricted out of the trickling filter. If wastewater backs up in the underdrain system, it could trap off airflow and lead to septic conditions within the filter. Now that we have identified the major components, let's take a look at three common classifications of trickling filters: standard rate filters, high rate filters, and roughing filters. Standard rate filters have a hydraulic loading rate of 25 to 100 gallons per day per square foot of media surface, and an organic loading of 5 to 25 pounds of BOD per day per 1,000 cubic feet of media. Most standard rate filters are dosed intermittently with the use of a dosing chamber and are not equipped for constant recirculation. Typically, standard rate filters utilize rock media at a depth of 6 to 8 feet. High rate trickling filters typically have hydraulic loadings of 100 to 1,000 gallons per day per square foot of media surface and an organic loading of 25 to 300 pounds of BOD per day per 1,000 cubic feet of media. Recirculation of wastewater is almost always used on high rate filters. Care should be taken when adjusting recirculation rates. Too high of a